Okay, welcome everybody to 52 Living Ideas. Today is one of the most ambitious meetups we're trying to do. We're trying to communicate what calculus is, why it is important in civilization, and what can it do for you for thinking. Okay, so that's what we're trying to do. Now, I'm delighted to have Stacey here, who's a mathematician. And Stacey, you just want to talk just a minute or so about your experience of teaching calculus to kids.
Sure. And mathematics in general to kids. So I'll use what Chase said about me is that I'm a programmer by day, mathematician by night. I'm a bit rusty on some things, so we'll see how that comes out today, because I'm probably a little rusty on some of the things we're talking about today. I had to go back and read stuff. Oh yeah, that's right. I remember that now. But I've had a lot of experience tutoring, and tutoring everyone from kids to adults. I've tutored adult college students. In fact, when my mother was going for her degree, I was still in high school and in college, and I was tutoring her and some of her cohorts as well, but in all forms of mathematics. Mostly I studied discrete math, so things like number theory, group theory, those types of things. But calculus has been one of those that I really loved from early on, and it was always a pleasure to get people to see and understand what was happening with calculus, this idea of math on a continuum. So that's kind of my background.
Excellent, excellent. So what I'm doing is that I'm a big fan of this book, Mathematics, the Science of Patterns by Kevin Devlin. That's the best introduction I've ever seen to mathematics. And it has combination of virtues, which is very rare to find in any book on any topic. Firstly, it is honest to God mathematics, very deep ideas of mathematics, and he's actually presenting those. Second, it is done in a very simple way, as simple as possible. And it's very accessible, and that's the work that I'm using as a framework for this presentation. So this is, this is the book, and the chapter is motion and change, and this is from page 73 to page 90 is what we are essentially covering. And I'm going to use most of Devlin's materials, arguments, and I'm going to do a kind of a quick version of it. I'm going to do a kind of an introductory version of it, and then I'm going to hand it over to Stacey to add anything. His knowledge is far vaster than mine. He knows these things much, in a technical level, his mastery of it is much higher than mine. So if there is a, difference, I thought it would be really good to hear two different voices on it and two different approaches to it. So let's get started. So what we're trying to do is that we're trying to make calculus accessible to everybody. That's what we're trying to do, and to show what the spirit of calculus is. That's all we're trying to do. What is this thing? So let me start. Now, if you're not already done so, please type in the chat your level of knowledge of calculus. You can either say 3 if you're very familiar with it and fluent with it, 2 if you kind of know it, and 1 if your answer is not really, I don't really know it. Okay, so you can go ahead. There is a 0. Wow. I know somebody always breaks the scale, so anyway, so that's where, so that way we can calibrate it. Okay, I'm going to start with this introduction. World consists of moving things. We are life. The world is constantly moving, and motion is natural. That's what the world is consist of. There is movement, and still life exists only in pictures and in imagination. There is no such thing as still life. Anything that you're seeing is basically formed by all these forces that are continuously in action on it. It may, like you think that table is, is still life. No, no, no. There is all kinds of things that are acting on the table all the time. Some of those factors are acting, and they are acting for sure. Like, and the biggest example of that is geology. Like you look at a mountain and you say, wow, that's a very stable thing. No, no, no. It's continuously in motion. There is stuff happening with the earth, tectonic plates moving. There is the wind, there is the rain, and that transforms things. If you want to see an example, see Grand Canyon. That's just river flowing. That's what it produces, given over time, enough time. So motion is fundamental, okay? Now, this is a profound philosophical point. This is the point about being and becoming. It's a question of, so much of the Western thought has been influenced by Parmenides, who basically regarded that it's the constant, that universe is constant and change is some kind of an odd thing that needs to be explained away. So as a side thing, and Plato follows in that footstep. So many of our ways of thinking is based on that. And so that's the background. Now, we are going to talk about all kinds of problems that these people like Parmenides and their followers like Zeno came up with. We are going to look at Zeno's paradox. But the basic thing to understand is that throughout most of the history, change was regarded as a problem, as something unusual, something to be dealt with. What I'm saying is that actually change, motion is natural. And if you approach it that way, many of the problems just solve themselves, okay? Now, calculus was the first attempt. It is difficult to do. So there is a tendency of saying, okay, I will hold on to the chair and I know everything that is going on. Hold on to a concrete and know what is going on. But you're doing that at the price of actually knowing what is going on, okay? People tried their best to understand motion and they failed again and again. And it was only with calculus, with really Newton and Leibniz, who really took the giant step of solving the very simple problem of motion. And that changed the world. So everything that we have, things like electricity, almost every technology that we have. So the way in which Kevin Devlin puts it is very beautiful here. Let me use that. So firstly, I'm going to read just a couple of paragraphs from him. So this is his take on calculus, or value of calculus. This one mathematical advance marked a turning point in human history, having a dramatic and revolutionary an effect on our lives as big as invention of the wheel or the printing press. Okay, the other thing I want to say here is that by introducing differential calculus, Newton and Leibniz transformed human life forever. Without the differential calculus, modern technology simply would not exist. There would be no electricity, no telephones, no automobiles, no heart bypass surgery. The sciences that led to these and most other technological development depend on calculus in a fundamental way. So that's what we are looking at. Okay, this is not a minor topic. This is really what we owe our modern civilization, the fact that we have the luxury of sitting in our homes, spread across America, even talking about such things, we owe to this. So that's my introduction of why we should be studying it and what it is. Stacey, what's your take?
Yeah, I agree. I'm going to I'm going to just provide a little contrast to your quotes, because I think that I tend to focus on things that are a little more wild and imaginative. So I'm going to quote Spock from Star Trek. Spock says change is the essential process of all existence. And even though it's, silly, it's Star Trek, and I know, you don't spend a lot of time with fiction, to me, that was one of the things that I remembered when I was a kid watching that. And, oh, yeah, that makes sense, because when, even things like breathing in and out, if you're not changing, you're not existing, and even then you're changing because you're probably decomposing. So that was sort of an interesting perspective. But what's kind of wild when you look at calculus and you look how it was formulated, and we'll get into some of this, the idea that mathematics mostly was machinery for capturing discrete things, moments in time or points. But if you look at an equation or a function, or, and we'll define those, they can't deal with the continuum all at once, not normally. And calculus gave us the mechanism for dealing with that continuum, sort of all at once. What I find interesting and fascinating is that when you start to look at some of the modern day physics and some of the things that we're picking apart, is that things that we thought were continuous seem discrete. And we may even have this notion, although it's really controversial. So, but this notion of quantum time, that is there this sort of smallest unit of time, super controversial. So, yeah, don't take that one like gospel by any means. But the other thing is that when you start to look at things from a different scale, they become fluid again. So take, for example, a tennis ball or one of those little plastic balls. It seems like a discrete thing. You have 2 of them, you have 3 of them, you have 4 of them. Let's say you fill a pit with thousands of them, and then you have a giant step into that pit. To the giant, that feels sort of like fluid. It doesn't feel like discrete, tiny little balls. So I think that's what what philosophers were sort of struggling with, this notion of how things were made up, and realizing as they were decomposing things that things seemed to be discrete and yet had this continuous property to them. And how do you marry that? How do you put those together? When you talk about Zeno, and I'll let you go into those, that was the fundamental issue with his thinking, is this notion of how do we reconcile discrete and continuous things.
Excellent. So let's look at the problems of motion. And the best person to do that is Zeno. He has actually 2 different paradoxes, one to do with discrete time and one to do with continuous time. So with the discrete time, he says, if the time is discrete, then any particular thing is at one particular position at that snapshot. And that is indistinguishable from a thing which is stable. So if that is so, how is it that the same thing is in a different place, whereas the thing that looked exactly like that, which was stable, continues to be there? So that is his paradoxes, thinking of time as discrete. But the most famous one of his is the Achilles and the tortoise. So here is the problem, as he states it. So Achilles, who is a very fast runner, and a tortoise, who is a very slow runner, are in a race for 100 meters. Okay. Let's say 1,000 meters race. Okay. Now, Achilles runs 10 times faster than the tortoise. Okay. So in the same time, so for example, in the time that the tortoise, and the tortoise, because it is slow, it gets a start of 10 meters. So it starts off at 10-meter line. Okay. So the race starts. In the time that Achilles crosses 10 meters, the tortoise has already moved 1 meter forward. okay? Now in the time that Achilles crosses that one meter, the tortoise has moved another 0.1 meter, and so on. So every time Achilles catches up with the tortoise has moved further. So the conclusion is that though Achilles is 10 times as fast as the tortoise, he can never catch up with the tortoise. So that is the problem. Stacey, you want to add anything to the problem before we go to the solution?
No, I think you stated it really well, and there are some alternate forms of it which we can talk about. But I'm curious if anyone has an intuition about the meaning behind this. Like, does it seem sort of like, is this stated correctly? Like, can this, you know intuitively that the faster runner is going to catch up and pass, but when you listen to the statement of the problem, it seems logically consistent that he can never pass. So I'm curious about people's intuition. I don't know if we can do that on a 1 to 3 scale or anything, but yeah, I think you stated it really well.
Okay.
Curious if people want to drop a comment.
Okay, if you have any comment, you can go ahead and drop it in the chat. So what I'm going to do now is I'm going to share my screen and talk about the solution to this. Now, I want to tell you in advance, if you can figure out the solution to this, you actually have the core idea behind calculus. Okay, it is it's as simple as this. Okay, this is what it is. Let me go ahead and share my screen. All right, can you folks see it? Stacey, can you see it? Stacey, can you see the screen? Give me a second. Stacey, you're on mute.
We can see it.
Okay.
Okay.
Yep.
All
I
right.
got it.
Great.
Sorry, I was
okay.
hunting
No
for the mute button in Zoom. It was coming up.
All right. So look at this at the top. So now at the top, we're trying to say this is the problem that we stated, right? So initially, this is how much distance Achilles is traveling in order to catch up. Okay. So he traveled 10 meters. During that time, the tortoise moved forward, then he went 1 meter, then 1/10 meter, then 100 meter, like that, okay? Now what we do is that we say, we're trying to add up how much he's traveled. So that sum we are calling S, okay? So S is equal to all of that. And dot, dot, dot means that it's going to continue on like this forever, okay? So the first formula we have is the distance that Achilles travels, S, is equal to 10 plus 1 plus 1/10 plus 100 plus 1,000, and so on and so forth, okay? The second thing that we do is that we divide that by 10, okay? So the S divided by 10. And when you do that, you can see when you divide all the numbers by 10, you get this 1 plus 1, 1/10 or 1/10 plus 1/100 and so on, okay? Now, the interesting thing is that you notice the pattern, that it's the same pattern. I have written it in a way where it is easy to see the pattern, that there is the same pattern that was there before. So what you do is that you say S is equal to 10 plus S by 10, which was that pattern over there. And now you have a very simple equation. You calculate it, and S turns out to be 11 by 11 and 1/9. So at 11 meters and 1/9 of a meter, Achilles is going to cross the tortoise, okay? So that's what it is. I'm going to just stop sharing the screen. Let me see. Okay, so that is it. That is the heart of calculus. If you understand this and understand the reasoning behind it, what it is trying to do. So notice what this whole process did. How is it different from what you were thinking originally? What you're trying to do when you're trying to, this mechanism is called an infinite series, okay? Which is like the foundation of calculus. What does infinite series do? What was the process that we used? We tried to identify a pattern. So again, you know, Kevin Devlin has beautiful words to summarize this. Okay, notice that the key to finding the value of the series was to shift attention from the process of adding the individual terms to the identification and manipulation of the overall pattern. In a nutshell, this is the key to handling the infinite in mathematics. So I'm going to share the screen again to show you the same thing here. So what we noticed is that there is a pattern over here. And we identified that pattern. It's the same pattern. And we came up with an equation based on the pattern. So this is the equation that we came up with. And that is what solved the problem. So it is identification of this pattern that enabled us to solve the problem. Okay, so that is really the heart of what you do in calculus. So let's take the time to understand this clearly. So Stacey, would you like to, can you elaborate, please?
Yeah, I think one of the key things is when you start to see things like that. So in that case, you have this series, you're adding all of these terms up, you notice a pattern, and what the mathematicians at the time were doing is noticing, I would say, what's called a meta pattern, a thing about those patterns. Some of those patterns that you would notice seem to get, say, in this case, smaller and smaller numbers. Doesn't really matter how many are out there, but they noticed, oh yeah, this is getting smaller and smaller. And the sum itself, if you were to just look at that sum, it's kind of going to a particular value. The technical term for that is convergence. So the series converges, and then we'll talk about another technical term, a limit, and some of those things. But other series may not. So you may have some other series, if you just did 1 + 2 + 3 + 4 + 5, that series does not converge to a value. So that's what kind of motivated this thinking was, oh, we noticed that some do converge and some don't. And it's crazy when you think about, like, you're taught in a semester or two of calculus some of these ideas that took hundreds of years for people to kind of make that leap, that intellectual leap, because it just wasn't the way people were thinking. So I think if you can see that in this example, you really are understanding the heart of calculus. If you can understand that idea that, hey, that thing kind of converged on this number, if I were to actually do the math and start writing it out, I would see it getting closer and closer and closer to that number. Of course, I can't do the whole thing, but by noticing the pattern, it gave us a shortcut of saying, oh, we can actually eliminate the rest of those terms. So to me, that's kind of the key intellectual leap here, was noticing what was happening with those patterns and going a little bit meta about it, a little bit one step up. And I'm going to add one little thing that I kind of ramble, but I'm going to one more thing. And I know people who have listened to me before talk about, I talk about sort of my universal way of solving math problems is to look at what I know and look at what I know about what I know, that sort of meta thing. In my day job as a software developer, it's kind of a similar thing is you have a level of indirection or a level above your current thinking that usually helps you solve the problem. If you're stuck in that level below, you're not going to solve it until you can jump above it and see the patterns and see the meta version of it. So I think that's really the key insight from here.
Absolutely. I think this is the, as you know, I want to pause here because this is really the heart of it. Everything that we're going to go, I'm going to tell you what we are going to talk about, but now we are going to take questions on just this point, okay? Because we want to make sure that this point is clear. After this, we are going to go into differential calculus. How do you, this is what Newton and Leibniz did of trying to figure out kind of slopes or gradients of things. Then we're going to talk more about the concept of limit that Stacey was talking about. Then we will talk about differential equations. We're going to talk about integral calculus. And then we're going to talk about the fundamental theory of fundamental theorem of calculus. So that's what is coming up. But all of it, and I'm going to keep, like a broken record, I'm going to keep coming back to this point, because if you get this point, then you get everything. Okay, everything is just details from here. Change of perspective, change of attention from concretes and concrete actions to patterns of actions. So you can project what happens and try to see where that projection is leading. That is what this whole thing is about. All right. So now we will take questions. So folks, go ahead. As always, type exclamation mark in chat, and there are no stupid questions. Okay. So feel free to ask any question. We are deliberately trying to have people talk about, we're trying to communicate this idea. I know it is very tough. I know it is something that has changed the world. So don't hold it back. Just go ahead and ask questions. So it's going to be John first, followed by Joe. John, go ahead.
It's is that number 11 and 1/9 an approximation that we're sort of just lopping off? Because, right, if the runner moves, the tortoise, like, you don't quite know the exact, to a certain degree, the exact point it passes. I mean, is that the idea? That you have to sort of, because it's so close for the convention of what we're talking about, we only really need to know that it's 11 and 1/9, but in reality, it's that series of infinite, 10 divided by 10 plus 1 plus 1 divided by 10 plus on and on for, infinitum. Is that correct, or?
Yeah, let me try to take that one. And I know there's some skilled mathematicians on the line. I saw lots of threes in there. So you'll forgive me if I'm rusty in my explanations, and I appreciate corrections if needed. So if those runners are ideal, that is, they're not real, real human and real tortoise, because, of course, a real human can't keep an exact speed. But if they are ideal, then that number is not an approximation, because if you notice what Shrikant did with that manipulation of the series was by manipulating it in a way where he said, okay, if this is the sum, and we can just pretend that we add it all up, even though we don't really have to. And then he took the sum and did the division and then the subtraction. When you do that, all of those other terms cancel out. And in a sense, it doesn't matter that there were infinitely many, because there aren't any more. They all cancel out except those first terms. And now you can just do the algebra on those. So it is to the extent that they are ideal figures, it is an exact number.
John, let me add something. This is a brilliant question, because that is really the heart of the whole thing.
Great question.
Okay, this is heart of the whole thing, and we are going to come at this issue in many, many, many different ways. When we look at the differential calculus, we're going to face exactly the same issue. When we go to integral calculus, we're going to face exactly the same issue. Okay. The idea is that you notice the pattern in which, so it's, it starts out as being kind of successive approximation. So if you approach it from an arithmetic point of view, right? When you start adding those numbers, suppose you are sitting down and adding 10 plus 1. Okay, now I'm going to add 10 plus 1 plus 1/10 plus that. You can actually do that. You can keep doing that. And that is a successive approximation process. That's the arithmetic way of thinking about this. So that is the previous way of thinking about it. What calculus does is that it rises one level higher, and it says, let's look at the pattern of what is going on here. Okay, so in the equation that we shared, I'm going to share the screen for a moment again. See, in the equation that we shared, right? What we did was that we essentially identified this whole pattern. Let me change the color of the.
I think what you don't see on that screen is the subtraction. Well, you see it, but he doesn't call it out on there.
Right. So this whole thing, right? It says this pattern is the same in both places, right? So it says the pattern is the same. So when you actually kind of take, if you take this 10 goes right here, right? And this whole thing, instead of, normally I would write this one here, but instead of that, I'm writing this one because I can see that this one is equal. So what it does is by identifying a pattern and just focusing on it, it converts an infinite series, the sum of an infinite series, into an actual number, fixed number, which is not an approximation. So this entire series is exactly equal to s by 10. And because it is exactly equal to s by 10, s plus 10, s is equal to 10 plus s by 10. So we get, surprisingly, it is an astonishing result. Okay, so I mean, the thing is that for, I don't know how many years, like maybe 2000 years, people puzzled exactly over the question you have, John. It's like, how is it? I can understand that this is maybe an approximation, but how is it that you can get an actual answer from it? And so that's what, but don't worry, what we're going to do is that we're going to come at the same issue from 3 different angles. So this is just the first way. We're going to go through it for differential calculus on gradients, and then we're going to do the same thing for area. And at the end of it, please let me know if that is communicated. All right.
Well, I think just quickly, I think it makes sense. Just that, you're sort of abstracting away the infinite sequence on both sides of the equation, so they cancel each other out.
Yes.
If they didn't cancel each other out, you'd have you'd have an approximation. But because they're equivalent approximations, you don't need to unwind it. You can sort of just say they cancel each other out. That's
beautiful. Yep. Exactly. That's
Got
exactly what is going on.
Yeah. Thank you very much. I wish you guys were around in 9th grade.
All right. Thank you, John. Thank you, John, for that question. Really appreciate that. Joe, go ahead.
Okay, so thank you for the qualifier that there's no stupid questions, because but the idea of, I had read something about heuristics and how they were like kind of calculated, and they were estimations, as John was just saying, back in Greece, in the time of Greece. But then I was trying to put this into the idea, the same thing of pattern. So if I were looking at it in a circle and I were calculating the pattern like in a circle, that would be, could I think of that as like a limit? The circle would be the limit, and then the calculus. What, did I lose you? Or did I
yeah, your sound is not very good. What I suggest is if you could shut your video and just speak.
Okay.
I think the voice will come off clearly.
Oops, sorry.
Go ahead.
So the idea of like estimation, and, you know, calculating exactly the patterns within a circle. And then I was thinking about within limits, the idea of limits within that. Is this basically just taking, and now I lost my question. So
Okay, let me try to answer it. Even if you lost it, let me try to answer it. So yes, the answer is yes. What you're trying to do is, for example, I mean, we're going to come to this when we talk about integration, but we're going to, I'm going to give you a preview of it. Like, for example, finding the area of the circle was a huge problem, right? I mean, it's a regular thing. How do you actually figure that out? So one of the ideas that I think this was Archimedes or Eudoxus, I don't know who they had a way of calculating it. Like they would put a triangle inside the circle, right, and they would put a triangle outside the circle, and they knew how to calculate the area of the triangles. So they said the area of the circle has to be somewhere between the area of this inner triangle and outer triangle. Then they would move to a square. Then they would move to a pentagon. They knew how to calculate areas of polygons, regular polygons. So they used that, and they would keep on adding the number of sides. And in progression, it went, you had a successive approximation of that. So it is the same kind of idea of the series. The series just goes one step further. As you know, I like this, you know, Stacey's term of kind of, you know, just one step higher, okay? That's all it is doing. It's saying, you go from there and say, okay, what are you doing when you are adding, going to the next polygon? What kind of pattern are we using? And can we use this pattern to figure out something regarding the limit of where these two things are going to tend to? Something like that. Okay?
That's exact. That was my exact. Yeah, that was the
yes, but we are going to, Joe, we are going to talk about it in detail when we come to integration.
Oh, okay.
All right. Next, you're welcome. Next up is Dave L.
Thanks, Shrikant. Thanks, Stacey. Yeah, I harbor some shame about not understanding calculus, having never learned it. My question is, how would you explain calculus to an 8-year-old?
Well, the good thing is that Stacey does this all the time.
Wow. So what I would do would depend on the topic and whether we were talking about you know, integral calculus or differential. So the place that this normally comes up when you're dealing with 8-year-olds, although I'm not sure that I do it all the time, is in when you're trying to figure out things like, oh, you know, how much pi do you have, or how much of this or that do you have, and this notion of, well, we know some formulas. And in fact, I was actually explaining this to someone who is an 80-something-year-old. We know some simple formulas for things like what's the area of say a rectangle, and we'll get to this. But the idea behind calculus, and I don't want to do a spoiler here, is take what we know and approximate what we don't know based on what we do know, and then make some successive approximations that get better and better and better. And if you do that, you see a pattern in those approximations. So calculus is more about this idea of, if I do something enough times, I get a more accurate result. And now if I look at that process, I can get the ultimate accurate result, because I can look at that process and say, oh, I know where it's going. I know where it's going to end up based on what the pattern looks like. That's a really non-technical definition, but that's sort of the basic idea. Is calculus is this idea of looking at these things that occur over time and seeing if you could find a pattern that leads you to an accurate result for the end. So sum, or we'll look at gradients or slopes in a minute, and we'll look at some of that. But that's really what it is.
Thanks. I was looking for a non-technical answer, so thank you.
Excellent. I will add just one thing. I would say the intermediate step is to get comfortable with successive approximations. See, what happens is that we, as human beings, naturally wants certainty. And there's, and that way of thinking ends up being a concrete oriented way of thinking. You either got it or you don't have it. Okay. First, you have to communicate to children that successive approximation is good, that you try your best and you know that you will be off. Okay. But you keep trying and keep, getting closer and closer. So that is the idea that's the intermediate step between getting fully to calculus. But this idea of successive approximation, philosophically, it is very deep, because what it is saying is that reality is what it is. I am trying to measure it. I am a limited creature. My ability to measure it is limited. I'm going to do my best. And then I'm going to see how far I'm off. And I'm going to take that feedback and I'm going to take the next step. And when I keep taking these steps, I'm going to get closer and closer to the answer. Okay. So that resets, that's different from the epistemological ideal of insight, of saying I have to be able to get it or not get it, or I feel disappointed that, oh, I don't get it. You should not feel that way, because that actually stops your learning. Because it is either you get it, in which case nothing more to be done, or you don't get it, in which case you can't do anything. Whereas this is a process of actually this worldly cognition, this worldly measurement. This is a principle of kind of measurement, or kind of, which is at the root of mathematics itself. And what calculus does is that it, in this sense, it takes this root of mathematics, which is about measurement, and looks at it one level higher, of saying, if you keep doing this, what happens? Identify a pattern in that. And that is why it is at a very, it is at a higher level than mathematics. All right. Thank you, Dave, for that question. Great question. All right. If there are no more questions, we are going to continue on. Stacey, this is going very well. I think we're communicating something. All right. So we will now go to the next step, is differential calculus. Okay. Now, differential calculus, again, I'm going to talk first in the simple way I can, and then I'll have Stacey talk about it. It's really, differential calculus is, firstly, you're starting by saying things are moving. Okay. And we're trying to see to what extent it is going faster. Okay. So let me again share the screen with you. All right. Okay. So now we're looking at an equation here. Maybe we should pause a little bit. Let me go ahead and unshare the screen. Maybe we should, Stacey, maybe we should talk about functions first. Sure. Can you talk a little bit about functions? Because see, functions also, this is another point that Stacey had made, is that it is moving from arithmetic. So most people think, whenever they think of mathematics, automatically they think of arithmetic, and all their intuitions are about arithmetic. This is kind of like moving to algebra, of you're trying to see kind of how does one thing change with respect to other, regardless of the quantity of this first one or the second one. What is the pattern of relationships between that? So what function tries to do is that it tries to capture that one quantity is dependent on another quantity, and that dependence is the same regardless of the quantity. So take a simple function like y is equal to 2 times x. So we don't know what x is. X can be anything, okay? Regardless of what it is, y is going to be 2 times that. So if x is 1, y is going to be 2. If x is 2, y is going to be 4. Again, this is algebra. Again, this is a major, this is not simple. This is a major conceptual advance. This was, I think it came partly through India, partly through Middle East, and it really changed mathematics completely. And it's a huge deal. Okay, the simple thing, y is equal to 2 times x. So that's what functions is all about. So go ahead, Stacey.
Yeah, let me, I'm going to share a screen now. I'm going to share my screen too here. Hopefully that comes up okay for everybody. And the notion of function actually is even more general than what we're going to discuss here. It goes into things like set theory and a whole bunch of other things that the other mathematicians will know about. For our purposes, we're going to think of a function. I have the handwriting of a mathematician, by the way, is a formula. But it's a special kind of formula. What it does is it takes some numbers, and let's just write some down just for kicks. And it maps those numbers onto another set of numbers. So let's say we're going to go to here, this one, here with this one, here with this one, here with this one. And so if you see that pattern, you kind of understand that, well, what he did was he just doubled the first number to get the second number. So let's call this first number, we'll just give it a name, x, because we don't want to keep saying the first number. That's just a long way to say it. And the second one, we'll call it y, because calling it the second number every time is just really cumbersome. So mathematicians don't like to say a whole lot of syllables, because when you're thinking about a problem in your head, all those syllables just mean time. So you're just going to slow yourself down. But we're just going to write down our function here, our formula, that is y equals 2x. Now, because we also really love our notation and our cool, language, and it's kind of cool because then other people can't read it. You're in the in crowd now, you can read this. We will say that y is a function of x. So we sometimes will say f of x equals 2x. That's just a fancy way of saying, oh, it's a function or formula where x is this unknown quantity. We don't really care what it is. We'll figure it out later. But we can plug in any x we want, use that formula, and get a y out. So y is just a function of x. Now, the way that I drew this here is kind of, it's okay, but if you really want to get fancy about it, you can say, hey, I want to see that more graphically. Some people are more visual thinkers than others. And so this cool little thing that was invented for doing this kind of graph, some of you may recognize it. The idea is for the x numbers, I'm going to put them down on this thing called the x-axis. Again, fancy term, doesn't really mean a whole lot. It's just where you're going to draw stuff. And then we're going to put the y's over here. And oh man, I'm going to be challenged to draw this curve correctly. But we'll start at like 0, and then we draw something at 1, and then here we're going to have the 2, and then here we're going to have the 6 is going to be up here somewhere. So 1, 2, 3, 1, 2, 3, 4, 5. Usually, not always, but usually you draw these so that the little steps that are in between each, the size of that is the same. So the step between 0 and 1, 1 and 2, 2 and 3, it's the same on the y-axis, that you get the same increment. You can actually do some fancy things where they're not the same, and it's kind of cool. But once you see that, you could actually then draw a nice little line. And my drawing is absolutely terrible, I admit it. But you could draw a nice little line to represent that so that you can kind of visually see what's going on with the function and maybe gain some cool insight about it. But that's really it. For our purposes, it's just a formula. It's just a way of taking a number and getting another number. In the case of this function, those numbers happen to all be integers. So if you want to learn some cool, fancy math terms, you're going to be at your next online Zoom dinner party, because who's going to do this in person? You can go, yeah, we were looking at functions that map from the integers onto the integers. So the domain and the range of the functions were the same, and just impress your friends with that kind of lingo. So we do talk about that, the domain of the function and the range of the function. The domain is this guy over here. The range is this guy over here, and we say that it maps from the domain onto the range. In this case, we're mapping integers onto other integers. So that's kind of it. That's what functions are.
All right, great. So Stacey, shall I go ahead and talk about this one next, and then
Sure.
I'm going to hand it over to you. This is very good. I think we'll do it twice. So I'll
Okay.
do it, and then you do it again. So there'll be two different voices. So I'm going to
All
start
right.
sharing the screen. All right, folks. So as Stacey described, we're looking at functions. So the function at the top right here, this is the y equal to x squared. That's a function. And what we're trying to do is we're trying to find the slope of the function. So both Newton and Leibniz, they're trying to figure out, I know that the function is, y is equal to x squared, but how quickly is it growing? So what is the slope? So they're trying to figure out what this slope is, okay? And this is what differential calculus is about. It is trying to figure out the slope. Now, why is this important in the first place? Because we've said world consists of motion, moving things. This is slope is a way of figuring out what is likely to happen to it. How fast is it accelerating? So this is about, instead of focusing just on speed, you're looking at acceleration. Okay. Instead of saying that, just saying, okay, this much distance is covered, you say, okay, how fast is it covered? So it's like, it is called the derivative with respect to time. So let's look at currently only with the concept of slope. So we're trying to figure out what is the slope of this function y equal to x squared. Okay. So here is how Newton and Leibniz did it. So you take 2 points on this curve. Okay, so this is a curve. It is, okay, and you're taking 2 points on the curve, P and Q. So P is at X here, and Q is at X plus H, whereas H is this distance between the two. Okay, so what is the slope? So you're trying to find, this is the slope, right? So this much divided by this much. Okay, so what is Q? So Q is going to be X plus H whole square. So that is the value of Q. Okay, because it is at here. Okay, P is at X, so that is going to be X squared. So this difference is this difference right here. Okay, and that slope is this. So slope is this divided by this part, which is H. Okay, now there is a standard way of expanding X plus H whole square. That is going to be X squared plus H squared plus 2HX. That's, just comes from, the quadratic equations here. So you use that over here, you plug this over here, and you get this result over here, okay? And then you divide it by H, and the answer that you get is slope is equal to 2x plus H. Okay, so that's fairly straightforward. I mean, we'll be happy to go through it again, but that's a fairly straightforward way of calculating the slope. Now, so far, there is no calculus here. Okay, this is just measurement of the slope. So what have we done? Firstly, this is a slope of a straight line. This is not a slope of a curve. This is slope of a straight line from P to Q. Okay. Now, where does the calculus come in? The calculus comes in when it says, let's look at this quantity h, okay? Suppose we kept on making it shorter and shorter and shorter and shorter, okay? As h keeps on becoming shorter and shorter, the difference, see, originally the curve was here and this was, let me draw it over here. Suppose the curve was here, the straight line was over here. As we keep on reducing the difference, the slope of the straight line becomes closer and closer to this actual slope at a point. Currently, this is P and Q are far apart. If h is large, then actual slope over here would be here this way and here this way. So that's quite different. Slope at P and Q are going to be quite different. But by making h smaller and smaller, through currently just look at the successive approximations. As you keep on making smaller and smaller, the slope will tend, slope between P and Q, the difference between that will keep on reducing, and it will come closer and closer to the slope of the line between P and Q. So that is the process that is involved in doing differentiation. So let me hand it over at this point to Stacy.
Cool. Yeah, let's talk a little bit about. I'm going to do this in a similar way, but I'm going to take kind of what I think was Newton's motivation. So Newton, looking at motion of planets and things like that, was really concerned about physical quantities. So he's looking at something like this, where he says, hey, there's time that's increasing and there's distance. And if I have some body that's moving and it kind of follows this function, this line that I'm going to outline here in blue, it kind of follows that function. Maybe I'm looking at a planet and I mapped out a whole bunch of points. I've got my little notebook and I mapped out a bunch of stuff and I say, man, it really does. I have a function I can plot and it looks like that. What he's concerned with is at a given time, how fast is this thing going? And you can do this on an interval, which is kind of what Shrikant did here. So this is that, actually I'm going to write that as a t, not an x, because we're talking about time. So let's call our little thing here t, and then t plus h. So start at this time, move ahead a couple of hours, h for hours. H could be seconds if we want, it doesn't matter. And how fast was it going there? And if I kind of look at the two, I can figure out how fast it was going in between, kind of what Shrikant did. But what about this little point right here? How fast was it going then? Well, really what I'm looking at is, and this isn't sloped well enough to see it, but there's a line that I could draw that just touches that point and no other point. We call that line a tangent line. Again, cool to use if you're at a cocktail party and you want to drop some terms, but that's the idea. And what Newton did, and there's some controversy about how Leibniz and Newton talked about this, and Newton talked to Leibniz about some of his ideas, and Leibniz published first. But of course, he also came up with a lot of innovations that Newton hadn't seen. So who's the father of calculus is always a big debate. They both are. But the idea is that if I can draw this line in closer and just squish the two closer and closer and closer to that point, then my approximation of this tangent line gets better and better. It may have started out as this crazy thing that hits a whole bunch of points and overshoots. Oh, my drawing is awful. Overshoots, but yeah, it was a little too big. But we got it down, we squeezed it, and then we eventually we're going to get down to a little tiny triangle in there that's like this, and then tinier and tinier and tinier. They get so much better as you go. I often say, and I'll say this again in the next section, this is what happens though when you have a mathematician looking at an engineering problem. Because an engineer would be really satisfied with saying, let's just take a measurement that's small enough that the building won't fall down. Let's make the measurement good enough to get what we need done. Figure out how much paint we need, or how much water we need, or how to get the building right, or whatever. And a mathematician's going to look at that summation and go, no, but I want an exact answer. I want it to be precise. I want the answer. So, you get the mathematician thinking about an engineering problem, and they're going to invent calculus and make the engineer's life a lot easier. But that's the idea, is this notion of we're going to just squish in on this thing until that slope is so close to that tangent line slope that it doesn't matter. And now, as mathematicians, we know what we're going to look for. Instead of just looking for that answer, we're going to look for one level up, patterns. That's going to be always the thing that we start to look for. All right, now we see a pattern. Is there a way that I can use that pattern to give me an exact answer? So that's kind of my take on it, is looking at the motivation that Newton had, which was really physics. And I would say Leibniz to a degree as well, but Leibniz had a little bit more of the theoretical mathematician aspect of it. They did a lot here. There's some things that they laid the foundations for that they never really saw through. So we'll see some of that coming up next too. That's my take.
Thank you. Thank you, Stacey.
All right.
So I'm very much partial to Newton because he's focused on actually trying to solve problem. And so I have read his paper on fluxions, which is actually very challenging because it's different. On one hand, it's challenging because it uses different terminology than what we are used to, because the terminology that we use is based on Leibniz. But he has a very visceral connection to the problem. So for example, one of my favorite things is that he calls these things fluents, fluents. So I love the term fluent, because that's like, these are flowing things. So another way of thinking of it, kind of coming back to kind of the root of calculus, world consists of fluents, and you're trying to grasp fluents. And he called the slopes fluxions. So whenever the fluents are transforming themselves, so that's so fluence is what it is. So now, coming back to the formula that I had, it had 2x plus h is what the formula gave us, okay? Now, h is a small quantity that we started with, and we can keep making it smaller and smaller and smaller. And as you make h smaller, no matter what x you're looking at, h can be made as much small as you want as compared to x. And you can keep doing this successively. And the process, and when you take it to its limit, h can be ignored. So then the slope becomes 2x. So this process of firstly thinking in terms of successive approximations, and then saying that we can make this as close to 2x as we wish. We can choose for any x. We can make we can make h as small as we wish, so that the slope is as close to 2x as we wish. This is the idea of thinking in terms of limits. Now, the interesting thing is that neither Newton or Leibniz had really systematically established the idea of limits. All they said was that this can be done successively, and you can make it as much. And Newton, he has a very good intuitive sense of what he's doing, and very effective. So for decades, probably centuries, I think a couple of centuries or so, at least a century and a half, there wasn't a kind of a systematic, rigorous defense of how do we, is it the right thing to do? Like people were still questioning. And then there were people like Cauchy, I don't know how to pronounce his name, and Weierstrass, who came along and provided this answer. And that this concept is the concept of limits. So let me hand it over to Stacey. Stacey, would you like to talk about the concept of limits briefly?
Yeah, actually, one of the things I want to do before we hit limits is just back on that formula that you had. If you can bring that back up on the screen, that would be great. Because one of the things when we talk about the rigor of this is that there were mathematicians who just said, hey, guys, your intuition looks good, but we need a rigorous proof. We need to know a little bit more, because look at that slope down there, that last line where the 2x plus h, and we can make h smaller and smaller and smaller and smaller. Now, who has the intuition to say, well, if we can make it as small as we want, let's just make it 0. And then we know slope is 2x. But if you look at the formula just above that, h is in the denominator. It's the bottom of that fraction. And that's kind of where we started and where we came from. So we better pick a value of h that works up there too. And 0 doesn't work there because we can't divide by 0. Doesn't happen, not allowed, breaks the rules. So you had a lot of mathematicians arguing that no, this is not rigorous. This is intuitive and it's fine. It kind of makes sense from that standpoint, but without rigorous proof, this notion just isn't going to fly with us. And that's where, whatever it was, 100, 150 years later, Cauchy and Weierstrass kind of came up with a formalism for the definition of a limit. The idea behind a limit is, let's look at the pattern of what's happening as h gets smaller and smaller in this and other equations. Now, this is just one potential example. But let's look at what happens as h gets smaller and smaller and see if we can formalize the mathematics behind that so that we can definitively say that there is a limit as h approaches 0 of this function. And now we can use that limit in our definition of the calculus of how we decide on what a derivative is, or what later we'll see some integrals, but derivative differential calculus, how we calculate that slope or that gradient that we're talking about, which will give us the point on that line. And if you go back to my picture, it was the speed at that particular point in time. That was what we cared about, is how fast that thing was going at that particular point in time. So that, I think the idea though there is that the notion of limit is formalizing what happens as h approaches to 0. And that's what Cauchy and Weierstrass did, was they came up, and I guess we don't really need to go through all of their stuff in detail, right, but they formalized it so that now we can actually definitively say the limit as h approaches 0 of that thing is actually 2x. So they came up with all the great formal math that now people said, oh, okay, we can accept this now.
Excellent. All right. So I want to just briefly touch upon differential equations before going into integration. So on differential equations, I just want to show you, let me see here. Okay, so what is I'm just going to jump. I think it's probably best to just touch upon this. So differential equations are, I don't know how to do this. So for example, what we're trying to do is to, let's say we're trying to see how do things grow. So for example, let's say take a cell that is duplicating itself every 2 minutes, let's say. Some kind of a virus, which is just duplicating itself every 2 minutes. What will be its trajectory? Okay, the answer, that's the kind of problem that a differential equation is trying to solve. That what will the next stage, what is the relationship between the differential and the original quantity. And this could be like, it can be of a complex differential equation with multiple levels of derivatives. So I want to, and it describes different growth curves. So for example, I just want to show you the growth curves that are described. For example, the one that I talked about, it would be unlimited or uninhibited growth. The one on this, this one right here. Okay. Now, some of the growths are that they start out like this, but they have some kind of a limit. Like, for example, if you're growing these cells in a dish and there is a limit of the amount of food that is there, there is some kind of limit to that. And all of these patterns are actually captured in these equations called differential equations. Some of them are limited growth. So it kind of moves towards its limit quickly, very fast, as opposed to slowly right here. But then it kind of goes as it reaches, comes closer to the limit, it kind of slows down. So these are kind of different patterns. Again, what we are seeing is that being focused on the concrete, that means you're just looking at this one particular point, okay, or this particular point, or this particular point, right? Thinking in terms of calculus, thinking in terms of sequences, thinking in terms of differentials and integrals are a way of saying, what is the curve on which this rests? And these 2 points, even if let's say that they are at the same level, same measurement, they have a very different trajectory. So knowing calculus and thinking about calculus is a way of thinking about not just what is right now, but how did it come to be and where is it going? And this entire practice of kind of differential equations is a way of kind of getting a sense of these patterns of movement. So this was kind of a very quick, don't want to go too much into differential equations, but this is my quick take on why it is worth, one of the big applications of this differential calculus. Stacey, could you add something?
Yeah, I'll be pretty brief, I think, but I will add a little bit here. And I'm also going to, give you guys some notation too to think about, because it's just cool. And even if you don't use it, like you'll be able to read this now. But we talked about these slopes or gradients on these functions. And let's say, this function is something moving. So we're just going to say that the function is called m. And that meant that we had like m of x equals, some number where we could get, we apply that function and we get another thing out, right? Everybody was cool with that idea, I think. So let's take that m and we say, oh, well, what we wanted to do is we want to find the slope or gradient. And so the way we write that down is the general slope or gradient of this. Oh, and actually I shouldn't put an x in there. Hey, nobody caught me on that one. Probably somebody did, but they just couldn't say anything. That was a t in there, and we had, just because that was time. So we're going to find the slope of m, and we say with respect to t, with respect to time. So we know kind of what the x thing was. So this is the way we write that out. And there's a bunch of solutions to this, but if you look back at the curve that we had up here, let's say that Newton went and took a whole bunch of measurements and measured and kind of figured out, okay, I can see what the values are. I need a function for that. The idea is to figure out what this function is. What is m? What's the actual formula for it? In this case, it might have been something like, oh, I did it again. I wrote x. So yeah, it might have been something like this because we had t squared. Figure out the formula that makes that work. That's kind of the idea. Find a formula for that unknown function is what differential equations are all about. And they're called differential because we're calculating this slope or gradient, which is also called a derivative. and or a differential. So one of these top parts is called, these are called differentials. So it's called a differential equation. Fancy term, but really it's just about, hey, can I figure out what function that is? It's not always possible to figure it out, and there are different techniques. The techniques get to be, some of them are easy depending on the type of problem, and some are really advanced techniques, but they can do some pretty amazing things. But again, you don't always have a way to compute it.
And these techniques of differential equations are used to calculate things like, okay, how fast is this virus likely to transmit? Or if there is a nuclear fallout, how long will it last, and what is the pattern in which it will grow? How are these populations growing? All kinds of issues like that. All right, so I'm going to again pause for questions before we go. So the final segment is going to be on integral calculus and fundamental theorem of calculus, which connects integration with differential. Okay, but I'm happy to take some questions. Is everything clear, crystal clear? You're all become experts in calculus, or do you have any questions? Again, there are no stupid questions. Want to just make sure it's a very difficult thing to figure out whether we have communicated. At least for me, it's very difficult to figure out whether we have actually communicated or not. So just feel free to ask any questions. I'm going to pause for a few seconds. Any questions? You can go ahead and type in an exclamation mark if you have questions. John, go ahead.
Is the statement all calculus can be expressed in terms of algebra and all algebra can be expressed in terms of arithmetic? And I guess, can all arithmetic be expressed in terms of logic? And so therefore all calculus can be expressed in terms of logic? True? And that so calculus is basically a different way of expressing these terms and making them easier to work with.
Wow, that's an interesting question. Not sure if I've ever been asked that before. I think I'd actually love to hear from some other mathematicians on this too, but I think there are some things where you have built the building blocks in the correct order, reverse order, but you have the building blocks right? You start out with logic. I guess you could be constructive about it, and you can produce essentially number theory, and then you can produce arithmetic, and then you can produce algebra, and so on. But there are going to be some things like the notion of limits that you express in terms of sort of an algebraic definition, but they're defining something that is a little different than the discrete kind of way that algebra works, I guess. So I think they all build on each other, to be sure. I'm not sure that I would necessarily want to express calculus in terms of logic without building up that language. It's kind of like the notion of all language can be expressed in terms of, or all English language, say, can be expressed in terms of letters. Letters make words, words make sentences, but you need sort of meaning behind those. You need phrases. You need a little bit more than just the letters for it to be a useful abstraction. So I think to some degree you're right, but I think there are some abstractions that go along with that. Notions of function, for example, mapping of certain symbols onto other symbols isn't just sort of a fundamental integral thing in terms of just logic. It's there to a degree, but the set of functions that you choose might give you a different branch of mathematics. You might choose a different set of what we call base assumptions or axioms to build an entirely new branch of mathematics on a system of logic. So yeah, I mean, I guess to a degree that's correct. I'm not sure what I would do with it though. Like where do I take that?
So one thing I would say, John, is that it would be a lot harder. It is the terminology and the concepts of calculus and things, these higher level things are optimized for for human beings to actually deal with it. Now, if it is possible to, the thing is that, these mathematicians, some of them are geniuses, like I've tried to read Gauss's book on arithmetic. What he does with arithmetic is pure magic, okay? But that arithmetic is not your arithmetic, okay? It is something else. And that is, but these particular higher level fields of mathematics, they spend a lot of time developing representations and concepts which enable you to deal with things in a direct fashion. So if you think that you are going to be able, it's going to be easier to get calculus.
No.
It's going to be at least 1,000 times harder.
Yeah, okay?
No,
it's more.
And it's not. So it's not a question to be kind of considered. It's not a reasonable possibility, though it may be possible to. That's a different thing. The
reason I ask is more for understanding than for actually like.
So the right thing I would say is that algebra sits on the top of arithmetic, I mean, in terms of. And calculus sits on the top of that is the hierarchy. So in order to understand calculus, you cannot really not understand arithmetic. So the dependency of concepts is in that direction. It is possible for some genius to come up with a way of kind of going back and doing something with it, maybe, but that's not something that is going to be useful to you.
Well, when I asked my question before, you broke it down into terms of algebra, right? So and that was helping explaining it. And like when we were doing with algebra, we break it down. So on some level, you're going meta, right? You're going between these levels to explain each other.
Right. So you have to go up though. You can't go down. You have to go up. I'm using algebra as to kind of say this is kind of algebraic thing, but algebraic thing was about seeing a pattern. But then calculus starts with that and rises one level higher. And that jump of being able to see what is the pattern of algebraic operations are you doing? And let me try to identify that pattern and think in terms of that pattern. So it's in that direction that the development is. Next up is Bob.
That was a great question, by the way. That reductionist question is good. I'm
John
still thinking
always
about
asks fantastic questions.
I'm still thinking about that.
He's been coming to my meetups for over 3 years. He's always asked fantastic questions.
Thank you. I don't always know the answers to my questions, but I take a shot.
That's good.
Thank you, John. Yes, Bob. What's your question? Bob, go ahead. Bob, we can't hear you. Looks like there is something wrong with your mic. All right, let's see. Anybody else has a question? Okay, so in that case, let's go on to integral calculus. All right, so on integral calculus, this is a very old problem. So I'm going to come back with, come back and look at, start with Archimedes, because he's one of my favorites. See, unfortunately, my math is very limited. I can get up to, like, I think 18th century, like Euler is about the limit of what I can easily deal with. And then I have pieces I can get into, it's like group theory, maybe a little bit or here, but it's very choppy after that. But so it is a pleasure for me to discover this work by Archimedes called the Method. And it's a very interesting story. It was lost. We did not know about it. It was actually a very interesting history. It's like, actually a letter written to a friend saying that this is the method that I actually use to figure things out. And then I express it in these different terms, as is the common, in the Euclidean manner. But this is the method that I actually use to figure things out. And this was just a letter that he had written. And during the Middle Ages, paper was very expensive and very hard to come by. So somebody had actually scraped out the writing of this method, the document on which they had, in order to write a religious text on it. In 1903, somebody kind of guessed there was something underneath this piece of religious writing. And it is called palimpsest, which is like the, when somebody writes on the top of another writing. And they carefully restored it. And that's how we got it in 1903. And it's fantastic because what it is that it is a way of doing integration. It's a very interesting idea. So I'm going to draw a little bit to show you. Let me see. To share the screen.
By the way, that's what happened to all my great works of math. Someone wrote over them. I discovered so much stuff that's gone now.
Was it that whiteboard or something else?
Yeah, it might have been,
Okay.
I don't know.
Okay.
It was papyrus. I was writing it all.
Okay, so I want to talk about, so when the best way to think about integration is think of it in terms of measuring areas. Just as differential, we try to look at it from perspective of looking at gradients or slopes. So let's take a circle. Okay, so we got a circle, and the first thing that we talked about was the method that the Greeks used to figure out the area of the circle. It's very difficult to figure out this. It's a smooth curve. We don't know what exactly it is. So what they did was that they put a triangle within it and a triangle outside it. So let's put it this way. And they knew how to calculate the area of this triangle and the area of the larger triangle. And the area of the circle would be somewhere in between that. Then they would go ahead and change to a square. They would put a square inside it and a square outside it. Now you can see that the squares approximate the circle area better. So, and then you go ahead and add a hexagon and so on and so forth. And you keep on getting closer and closer to the area of the circle. The second way is let's take a parabola like this. And we're trying to figure out the area of the parabola. They knew the curve of what they knew the equation for the parabola. And what they would do is that they would divide this into, I'm going to do it this way, into different squares where they tried to get the, let's put it this way. I'm just put it, sorry, I've changed the thing here. So just basically dividing it into different slices. And if you try to make the slices closer and closer, smaller and smaller, and added up the area of the slices, you will be able to approximate the area of the curve. And that's the general method that was used to find the area of the curve. And this is basically what integration is about. You're trying to say, what is the area under a curve? And I will try to relate it back to the general themes that we are talking about of calculus. But I just want to point out just one thing here. I'm going to give the kind of detailed presentation to Stacey, but I want to point out one thing here. The process of saying, you saw this in case of circles, the process of saying, a process of successive approximation is the same idea as the Achilles and the tortoise. You're continuously making successive approximations. And at each stage, you are coming closer and closer to the approximation. So that's one idea of successive approximations. The second idea, that's the same thing that we used in our with our slopes. We tried to keep on making successive approximations here. That's the same kind of thing we are doing here or here. We're trying to kind of divide this into smaller rectangles to kind of get closer and closer to the area. Then, so that was one idea of successive approximation. Then try to figure out the pattern of successive approximations in order to get an exact number using the concept of limits, okay? This process remains the same for the series, for the derivatives, and for integrals. That is what is common. And if you get just that it is successive approximations, and by noticing the patterns of successive approximations, you can come up with the exact measurement. That is what calculus is about. Okay, so I want to just talk about it at this level, and I'm going to hand it over to Stacey for details.
Yeah, I think you did a great job. I don't know that I have a lot to add. What I would probably do is just kind of point out that there are a couple of ways to approach this. So the idea, again, if you kind of go back to that curve, hey, that's my best drawing to date, is you're going to draw those rectangles so that each rectangle is about the same size. They're going to have, one side of it will be coincident with the others, but each one is going to be roughly the same width, say on the x-axis, but they're going to have different heights. And you're just going to continue that all the way across. I'm not going to draw all of them because I'll be here for a while. You can do this with other shapes too. Rectangles are easy. There's something where you can actually do this with a sort of, I guess, trapezium or whatever, where you have the rectangle with the little triangle part on the top as well. But the notion is you're going to have a bunch of those rectangles going across. You can figure out the width because you made them how wide you want it to be, that step size, you made that up. And then for the height, you can just say, oh, well, we're going to take that first x coordinate, compute the value of the function there. That's going to be the height. And we do that for each one. And so now I just have a simple sum to get the area. So it's going to be the width of x times the height for y times the number of those that I have. Hopefully that makes sense. So just kind of computing all of that up, or actually adding up the number, not multiply, but add all of those up. So it's a simple sum. You keep adding more and more and more. And as Shrikant pointed out, that's going to leave a little gap. I'm going to leave out this little bit in here for each one of those. So what do I need to do? Well, I need to make that smaller, that gap smaller, to get a better approximation. And a better approximation on top of that would be make that even smaller. And if you remember that little h that we had earlier, that we then took to a limit, what we're going to do is say, let's just make that so tiny, infinitesimally small, so that we essentially have infinitely many of these that are infinitesimally small. Obviously, we're not going to do that calculation. We're going to look for a pattern. And we're going to look for the pattern that gives us that approximation over time, that gives us a better approximation. And using that limit idea, we'll be able to come up with the exact number for this area under this curve. And I think that hopefully that makes some sense. That kind of summarizes the idea, is that just using successive approximation and then applying limits to the pattern that we see.
Excellent. Thank you, Stacey. So that is a quick overview of integration. Now, for the finale,
the grand finale,
it is called the fundamental theorem of calculus, and I'm going to have Stacey explain that, because it's really one of the biggest things that people realized. Go ahead, Stacey.
Okay. Let's see. I haven't really explained this in a while, but let's say that we. I guess I'll share my screen again, and I'll do my best on explaining this. I'll probably make a terrible explanation, but
okay. And Stacey, let me just say, Stacey, let me just say one thing.
Sure.
So I mean, let me give away the punchline first, so
Yeah.
people actually know where it is going. So the punchline is very simple, that it turned out that, people figured this differential calculus out separately and then integrals separately. So integrals, for example, Archimedes had worked on too. What they realized that derivatives and integrals are inverse operations. And that is really, stunning kind of integration. And that's what the fundamental theorem of calculus is about. Over to you, Stacey.
Sure. So I'm going to start with, we have some, let's say we came up with some formula for computing the area under the curve by using that successive approximation technique, applying a limit and coming up with this idea that, hey, we've got an area under the curve here for this f of x. So y equals f of x over here. And we'll just make it a little bit more explicit. I apologize for my terrible handwriting. So y equals f of x. Okay. So we came up with that, and we said, okay, well, let's take a look at really what happens if I go back to what I was doing before and say I want the rest of this area as well. So I start out at x, I move over to x plus h, right? So now I've got this x plus h part in here, and this is a little rectangle, but I could say something like the area at, say, x plus h, and I'm going to take that, and that's going to be equal to the area at x, so this part here, plus this extra bit in here. And that extra bit is going to be, so the size of this is going to be h, because that was x plus h, times the height, and we know the height of this thing is, maybe I should draw that a little bit better, sorry, times f of x. And this might look a little bit familiar. If you start to mess around with it a little bit, what you end up with is a of x plus h minus a of x divided by h, and that's equal to f of x. Do you remember what Shrikant wrote earlier? That was the gradient, the slope. So what we have is that f of x is the slope or gradient of our area function, the function that gives us magically what's in here. Now, we haven't graphed a of x, just to be clear. This graph is showing f of x. A of x is this whole bit down here. If we were to graph it, the graph would look a bit different than this shape that we have here. But what we've noticed is that, hey, that's the derivative, that's the slope of this a of x function. That means that if I go the reverse direction, what they used to call an antiderivative, right? If I go the reverse direction from starting with f and figure out what function has a slope that matches f of x, that function will be the one that gives me the area. So by going kind of the reverse direction, I can get that area function. Well, now we already figured out the area function earlier. We were doing that with the successive approximation and the limit, and we figured out the derivative earlier, the slope function earlier. And this thing just basically ties the two together. It says if you take the derivative of the area function, you get the one that shows you that is this f of x itself. That's the slope of the area function. So tying together the sums and the gradients is the fundamental theorem of calculus. It says basically you can go both ways. You can go from a derivative to this sum, and by the way, the cool party term for that sum, the sum is an approximation. The cool mathematician is going to give you an integral, which is going to be the exact number. But think of them as similar or equivalent. The sum is what mathematicians call the integral, the area of under that curve, area under the curve, AUC. Man, my U looks like a V there. It's a Roman U. The area under the curve is that integral. So fundamental theorem, we can go either direction. If I want to find the area under the curve, I can integrate F and figure out what A is, the function that gives me the area under the curve. So that's really it. That's the idea behind the fundamental theorem. I can go either direction. There are mechanisms for doing it. The way that you do it depends on the type of equation. And I think in Devlin's book, he kind of shows how to do that with sort of simple, what's called polynomial equations. Equations that basically are, say, x raised to some power. It becomes really simple. And I think he shows how to do it also with I think he does sine and cosine and other functions. Another book that's that gets a little more deep into it is a book called Calculus Made Easy, which I grabbed off my shelf while we were talking. This one is actually, we talked about Martin Gardner earlier. Martin Gardner took this book, which was 75 years old, and he kind of helped update it and add a few things to it. It was really originally done by Sylvanus Thompson. But this is actually a really good book if you want to just kind of learn more details about what we were talking about and get a little more technical. I also have some links that I can share with Shrikant, but I can put them in the chat actually, for some things that if you're playing around with this stuff and you get stuck and you just need a little help figuring some things out, there are some online calculators that will help you. And there's some tools for like drawing out figures and some math editing tools. Wolfram Alpha is one of my favorites, but I also put some in here that are a little easier and more approachable. But if you start to play with some stuff and some actual numbers and equations, and you get a little wrapped around the axle, those will help you quite a bit. I especially like the first one because it's an app you can put on your phone too.
Excellent. So now I want to just wrap up very quickly. So as we're saying right in the beginning, this is not a minor issue. This is, we are living beings, and thinking of us, for example, this has tremendous implications about thinking about everything actually. And what I'm going to do in the next meetup at 2:30 is my friend John has been working, he's has been a fitness trainer, and he has been thinking deeply about health. So he has all these principles of health. And one of the things I'm going to do is that I'm going to express all of them in calculus terms. He's going to present all of them, and then we're going to talk about it in terms of integrations and differentials and what is it that you focus on. Essentially, to give you like a preview, is that lots of problems in health come from looking at concretes and not looking at sequences, not trying to calculate the integrals of things, and refusing to work on the differentials of things. So it's kind of being able to do differential and integral calculus about your health is what being healthy is all about. So that's what we're going to talk about, because I want to apply some of these ideas in a commonsensical way. So that's coming up at 2:30. But now we are ready for questions. So folks, we've got 4 rules. Number 1, if you have a question, go ahead and type a exclamation mark in the chat. Number 2, keep on topic. We're talking about calculus. Number 3, be brief. And number 4, feel free to disagree with anything, speak your mind, but do so courteously. All right, so questions. What, no questions? I can't believe this.
Everyone's busy doing calculations. Calculating all those things that they always wanted to.
Wonderful. So Dave, go ahead. You're first.
Thanks, Shrikant. And thanks, Stacey. This was a really great presentation. So I was just wondering, I believe you're in software, Stacey. How does calculus come up in your work and in your daily life? I'm just curious, aside from, being a class that everyone takes in high school, most of us. Yeah. So
that is a great question. And there's some things that I think distinguish my software career from others. So I was not formally trained. I taught myself software development. And I've always used a more mathematical approach to it than the programmers I work with. In general, the math that had been coming up for years was more in terms of things like algebra and set theory. For people who have a background in it, using relational databases is basically set theory. Lots of algebra and discrete math and group theory kinds of things. Lately, however, people probably hear about AI and machine learning and neural networks and all of these great things. We actually use calculus. In particular, we use gradients, so those slopes of curves that we were talking about, to help find what's called a local minima of a function. So when you had those functions that we drew, they were kind of straight and simple, or they had one little curve. But imagine a function that goes up and down, and it has peaks and valleys all over the place. When you're building a neural network, what you're doing is you're giving it data, you're training it in a way that says, hey, if you can find this low point on the curve, you're doing really well. You're really close to the right answer when you do that. And we use what we call it an algorithm called gradient descent. Basically, think about if you were walking around in the hills and valleys and you wanted to get to a low point, you could actually do it with your eyes closed, because you would feel the slope. Well, if you didn't trip, that is. But you could feel the slope, and you could kind of walk down in the right direction to get you to a low point. And at some point, you would just feel around with your foot and realize, hey, every other direction kind of goes back up. I must be at a low point. So that's the idea behind gradient descent, and it's an algorithm that was based in calculus and this idea of finding gradients to functions. We tend to do it with functions that have thousands of variables at once over many layers of what's called a neural network. But it is a really good technique, and the leg up that you have if you've understood calculus is that you understand how neural networks work a little bit better, whereas my programmer friends who kind of didn't do so well in math, they can use the tools that other people build for them, but they can't really understand what's happening in those tools.
Thank you, Stacey. Next question is from John. He asks, are both derivatives and integrals essentially extrapolations?
Extrapolations in the sense that you mean that they are estimates. So the idea again is that you go beyond that, they're not estimates in the sense that we formalize the concept of a limit. So when we started to look at derivative, for example, we said that, hey, it approaches this value as h, in our case, approached 0. But the formal stuff that Cauchy and Weierstrass did was to show that, hey, if we formalize limits, we can actually show that that is the value, that we actually can come up with an actual value for it, for the limit of a function. So we use that limit of the function as say in this case h approaches 0. We use that limit as the answer. So I wouldn't say no. I wouldn't call them. So extrapolation and approximation, I'm using them the same way, and they're not really the same thing. You can extrapolate to get the correct answer and to get an exact answer, but we used successive approximation to lead us to that point. Hopefully that makes some sense. And if anybody wants to make correction to that, jump right on it.
Okay. I mean, I think what he was thinking of by extrapolation, John is a good friend, so I might be able to guess what he's thinking of. Extrapolation, especially he's thinking of integration. of saying, is it all about kind of figuring out if a curve went like this, where will it end up in the future? Is it all about trying to compute a result of a certain trajectory across time?
Yeah, I'm not really sure if I understand completely that question.
That's fine. That's fine. Let's go to the next one.
That's interesting. Yeah.
Crystal, I know you came in late. We're talking only about calculus. You have a question about calculus?
It's not really a question. It's just regarding the last question about extrapolation. I found a useful idea, anyway, is that when we take a derivative, we're kind of taking a dimension out, and when we take an integral, we're adding one in, sort of. And that just helped me to visualize things better, like the derivative of x squared is x. So if you think of a square as being the product of two sides, then what would be the slope? It would be one of the sides, and sort of really simplifying things. Or if you were to take volume of something, then you would cube the sides. So that's sort of what we do with derivatives and integrals, if that helps at all.
Okay. Next up is Joe, followed by Bob.
Thanks again, guys, for doing this afternoon. This really is, it's starting to bring context to things. I have a quick question. Maybe could you give an example of how limits work within a neural network? Like a specific concrete example, maybe, and no problem if it's too abstract.
So, yeah, and again, I offer other people to chime in on this, but more so in terms of computing slopes is what we would do, not so much directly trying to compute the limit of a function, but we're more looking at the slope of a function. So what happens in a neural network is you feed a neural network. Let's say you're doing something that recognizes number forms, which is one we had to build. I did an online Stanford class that does this, where you have pixels in a box. So you draw the number and you divide it up into dots, and you look at those dots and you encode each one of those little dots. They're called pixels. You feed that to the neural network, and you have some functions that you use, and we get into a whole bunch of stuff about the functions. That's a lot more complex. But at the end of it, you get some answer. And the answer might be wrong. And you give the thing a 9, and it comes out and says, hey, that's a 2. You can actually look at and what the neural network came up with in terms of its what we call weights on the number form. So 0 through 9, and it says, hey, that's an 80% chance that that's a 2, and it's a 2% chance that it's a 9. Like, that's really crap. That's the wrong answer. So we figure out how wrong it was, and we do that with what's called a cost function. So we say, oh, here's how you deviated from the actual result. And so we have these marked results where we say, this is the training data. These are the things that it should come up with. Here's how bad it was at figuring that out. That cost function, and there are different cost functions you can choose. But by minimizing that cost function, we improve the accuracy of the neural network. Minimizing the cost function, if you think about this for a moment, is finding a low point in the function. So if the function is a curve that moves up and down, I'm finding a low point in that function. That minimizes the cost. Now, it may not be the best, but it's local. It's one that I can find, because there may be lower points other places in that curve that I just don't find. But by using the gradient, so doing some calculus and computing the gradient or the slope, I know which direction on that curve I should be moving, and I can adjust my neural network accordingly. So that's the idea behind gradient descent, is I can come to a locally good answer to minimizing that function. It may not be the globally best minima for the function, but it's locally one of the best. Finding the global minima is hard and sometimes not possible with numeric techniques.
Thank you, Stacey.
Thank you.
Next up is Bob. He doesn't have a mic, so he asks, is the exact definition of what a limit is too technical to say? What is the definition of a limit?
Wow. So I was actually going to bring up, yeah. I mean, I'm not sure how to say it.
That's fine. We can skip it.
I mean, there's an intuitive definition. Actually, I'm looking right now. I was looking at the Wikipedia article on it just to see if there was a better way to say it. There's sort of the idea of function converging to a point, and looking at some of that stuff. It may not be, but I don't really know if I have the right words to say it in a non-technical way.
Okay.
So if someone else does, please type it in or let us know, because I'm just not thinking of a great way to say it non-technically.
And that's fine. I mean,
basically
I think
it converges to a point.
I just wanted to say that, you know, Newton and Leibniz did fantastic things, and we were able to build a lot of things without having a technical definition of limits. I mean, of course, it's well worth doing, but it's a separate thing. I think you first, I mean, if you're trying to kind of grapple with it, first you need to get the idea of, you know, the ideas that we're talking about, and then, you know, kind of the work of Cauchy and of Weierstrass is critical, but that you can pick up later on. It's like the justification of saying, okay, why? It's like the reason of why it works. But that it works, you need to get that first.
Yeah, and I think that's right. I think, so the best sort of non-technical definition I can give is that there's a value of a function. So we have a function of x, and as x approaches some input value, the function itself approaches some output value. So the x's and y's that we were looking at, as I change x to approach some value, that y is going to approach another value. And so we say the limit as x approaches, say, x plus h or c or whatever, equals y. So we can see where it's going to go. That's a sort of the informal, non-technical definition. It gets a little more technical, and then the computability of limits is a whole different topic, because computability of limits changes based on the types of functions, and it's not always easy to do as well.
All right, John, you had a take on the point. I also want to get back to you, because I said that, you know, you asked the best question in the beginning, because that really went to the heart of this whole thing. Yeah. And I don't know whether we have done a decent job of answering and explaining on that. So please.
I will. First of all, I think you've done a phenomenal job. Like, I feel like I've gained more understanding of calculus in like 1 hour than all through college. Like, you basically just went through an entire undergraduate curriculum in calculus that was, when I remember looking at these classes, were like just tremendously intimidating. And it's not that intimidating, it's just the labels. But getting back to your question, the question around this sort of what limits are, it seems like it relates to my original question, and I was reminded of the sort of map paradox, or the coastline paradox, in which like the more accurately you map a coastline, the longer it becomes, right? So you map a coastline, let's say the coastline of Britain, at a certain resolution, right? Certain number of lines for those little curves, and let's say it's like 2,000 kilometers long. If you double that resolution, it becomes 4,000 kilometers long. So the problem is that the more accurately you map it, the longer it becomes, and it eventually becomes infinite, which doesn't make sense because the coastline. And so I think, is that sort of what calculus sort of gets at, is containing that infinity so that you can actually accurately map that coastline?
Yeah, I mean, that makes sense. That I guess there's some that's a pretty reasonable way of looking at it. what you do is you kind of basically restated Zeno's paradox in a slightly different way, and kind of came up with the solution for that paradox on the coastline as well. But yeah, that makes sense.
Thank you. Folks, it's about 2:05, so it's time for takeaways. We're going to go directly to takeaways. So I'm going to go in the order in which I see people on the screen. You're welcome to type in skip if you want to skip. So let's go with Gary, MP, and John first. Gary, go ahead. Do you need more time, or are you okay?
I'm good.
Yeah,
okay. Go ahead.
Definitely wanted to thank Stacey for the explanation, Shrikant. Revisiting was really cool because you laid out the goal of what I could expect to see, and it makes it so much easier when I understand, the big picture goal. If I want to go through it, I would know what I'm working towards. I took calculus, and it was never approached in here's the final cake that you get to make. That you showed those processes, so I would be able to understand where I'm going versus it was just manipulation numbers. So really appreciate it. I definitely think I would rewatch this recording because you so succinctly put pieces together. So I definitely appreciate your investment of time.
Thank you, Gary. Appreciate that. Next up is John, followed by John R.
I'll skip. I think my
okay.
comment around this being awesome.
Sounds good. So John R. followed by Dave.
Well, thank you. It's a lot of fun to revisit some of these things. I took a lot of this in college and whatnot, and structural engineering, and it gets interesting because here we're essentially talking about pure math. And when you get into the notion of engineering, then you're talking about how these ideas help you deal with specific physical problems. And then the next leap takes you into probabilities, because these notions can be applied, but when you start worrying about material properties, then material properties are notoriously hard for us to understand totally. And physics, of course, will take you there. Will tell you that this is difficult. So you end up with probabilities, so that you're always eliminating the problem here, the essential philosophical problem here. This is not mathematical anymore. This is philosophical, but this is where my head is going. Is that once you make that leap of saying, okay, here's this pure math, and we can apply it to physical properties, then you're always jumping at the center, and you're cutting out the extremes. But we know that the extremes happen. So once one says, I'm interested in the extremes, and in addition to how I'm interested in the most likely probabilities, then all kinds of interesting things happen. But we're way beyond the limits of this talk. So thank you for letting me ramble a little bit.
That was very cool.
Thank you, John. Next up is Dave, Yi, and Wen. Dave, go ahead.
Thanks, Shrikant. Thanks, Stacey. I'm fearful of math, and this made me approach it a little more. So I'm grateful for that. I'm going to check out the Devlin and Thompson books. I think my one-sentence takeaway is that calculus is abstracting from past data and using that to predict future data algorithmically. That's my takeaway. Thank you.
Thank you, Dave. Next up is Yi, Wen, and Mike.
First of all, thank you, Shrikant. I never see calculus being discussed this way. The reason I came today is because the connection between calculus and philosophy. So what I like about today, I learned the most out of it is actually what Robert said. Don't confuse the number of steps by the size of the steps. So for the first question that you mentioned, I never thought about this way, that you never think you're going to catch that person, but if you look at the total number of the distance, it's not that far. but then we're afraid by this number of steps rather by the size of the steps. Thank you.
Thank you, Yi.
Nice.
Next up is Mike, Randa, and Audrey.
Well, the biggest takeaway is that the difference between a local optimization and a global optimization is very complex, and you've described it as very complex. The technique that I have used and that I think of in both in math problems and in psychological problems is to map it into a different space. So you can convert a nonlinear problem into a linear problem, a higher order problem into a linear problem, and then it may not guarantee an optimal solution, but it will often come much better, give you a much better insight into the problem.
Absolutely, that's a good point, and that's
Loss
actually one of the
transforms
techniques.
is another name.
Yep. Great.
Thank you. Mike, you're a man of many talents. You always have really fascinating things to say, no matter what topic, what subject, and who we're talking about. So,
well,
thank you.
It turns out that that's the only area I know is the language of math pulls many talents into many different problems.
Thank you.
So that's the and that's probably what Stacey has found too.
Yep. Absolutely.
Enjoy. Thank
Thanks.
you.
Next up is Audrey. Audrey, would you like to add anything? Okay. All right. Stacey, I'm going to give you the last word. What do you think?
Well, I enjoyed this again. I appreciate it. I love the comments that people made. I highly recommend checking out Devlin's book. Devlin also has a series of talks. I think you can find them on YouTube on mathematical thinking. It's a free lecture series. It even has some downloadable material to go with it. But that would be kind of a fun one too. He's a really interesting guy to hear talk. That's it, really.
Sure.
Check out some of the links I sent. Let me know what you come up with.
Yeah, let's pause for a second. Crystal, you had a question. Go ahead.
One more.
You had your takeaway for this.
Oh, well, I just wanted to say thanks again. I did send you an email, Stacey. I don't know if you received it or not, but just in case
I saw your note. I just saw your note, and I'm just really slow about doing personal emails, but I'll get to it.
Okay.
Yep. All right.
I just wanted to make sure you got it. All right. Thanks.
Sure. Yep. Thanks.
All right. So I want to say one thing. I am very pleased with this presentation, Stacey. I thought we did a decent job of describing kind of the motivation behind, and I think, like for me, this is a big passion. I know it is for you too.
Oh yeah.
But I think that math is a part of the general toolkit that everybody, if everybody had it, they would be able to do a lot more about pretty much everything, because it's all about just measuring things and kind of thinking about things in a more systematic way, and kind of focusing, kind of moving from like having your eyes right next to the thing to kind of stepping back and taking a bigger picture. So math in general, as you pointed out before, it's kind of rising in the level of abstraction, and it's very similar to what you do in thinking in general. So there is a lot of carryovers between math concepts and thinking itself, and there are just profound relations. So that's that's great, and so it worked out really well, Stacey. So thank you so much.
Yeah, I enjoyed it.
I really appreciate this.
Definitely fun.